Welcome to Renewable Energies. I hope you enjoyed the last lecture. I think calculating the geometry of these blades, that this is one of the little gemstones in this course and in physics in general, I would say. Let me pick up where we stopped last time, and let's look at the formula that we derived. So here we have this formula. Yeah, so what we calculated was the depth of the blade, independence of the radius. So maybe so here we have such blades, yeah, and we were calculating this length here, the chord length in technical terms, as a function of the radius, and we found that so that the higher the tip speed ratio, right? This is the tip speed ratio. The higher the tip speed ratio, the shorter the chord length. And you see here this dependence R over capital R, where capital R is the length of the blade, the radius of the wind turbine. Very nice. Now we made a few remarks here, yeah, so that for fast turbines this term here can be neglected, and that it's also kind of an approximation, yeah, because this thing here may not be a constant, and so on and so forth. Now to finish, so the last but one point here would be to look at this diagram, which is actually called Hütter diagram. So what you see is that we plot the ratio of the blade surface to the surface that is swept. And if you think about a modern windmill, then we know that the chord length is very small. Therefore, the ratio of the blade surface is very small so the ratio of the blade surface is quite small as compared to the area swept by these blades. Yeah, and this is what you see here. Yeah, so here we see the percentage of this area, and if you go to slower windmills, then you see that the area of the blades gets much larger. I'm perhaps not I wouldn't entirely agree with this, but let's look at a few examples. So first of all, here is Hütter. Yeah, so Ulrich Hütter, and if you read his biographic data, then you see that he was a young engineer in the time of the Second World War, and actually he was working in this area at the NS company Venti Motor in Weimar. This is their test field in Weimar. I don't know where it exactly was, but this is a historic photo. And what this Nazi company tried to establish, so it was founded by figures like Saukel, so the local Duke here, so to say, the local Nazi Duke, who was later executed in the first row in the Nuremberg war criminal process or a trial. So they tried to establish such decentralized windmills for electricity generation not for a good purpose. Yeah? So the idea was that the conquered regions in East Europe There they would place German farmers as a defense outpost or so. And of course they need electricity, and in this huge land, they thought that this would be the solution. Actually, I also have a little bit of family background of that. So my parents and my grandparents, and well, actually the grandparents also, of course, they were farmers, and the Nazis wanted our family to be such farmers going to the east, actually to Poland. But my grandfather, he resisted. But actually, on our little farm in Franconia, there was such a windmill. It was used for water pumping, actually. So, and Hütter was the person to build this, and he was actually also a member of the Nazi party, probably just for career purposes. It's not known that he committed any crimes. And well, but in 1943 or so, when the war went south, when the war developed not in the favor of the Germans, they stopped these activities, and Hütter was reassigned, and so he developed aircrafts, so military aircrafts. And after the World War, eventually he became professor in Stuttgart, and he picked up on his earlier research on windmills, and he invented all the modern designs that made wind power actually well, a mature technology. So he was called the Wind Pope, the Wind Pope, and he influenced all the successful approaches. And you remember the Grovian windmill, the failing Grovian windmill in Germany. They asked him initially, but didn't take his advice, and well, it failed. And I think I gave you one quote from the newspaper Die Welt, conservative newspaper. So in an article they advertised his biography. Would be interesting to read at some point for me. Okay, and this was one of his early windmills, and you see the geometry of these blades, but there was much more. So he was building lightweight, and people at his institute said, well, whenever you came there, it smelled of this epoxy and glass fiber composite stuff. Okay, but now let's look at a few windmills that we could place in the Hütter diagram. So this would be here a modern windmill, Enercon windmill somewhere. You see them in different stages of construction, but this one here is already operating, and you see this small ratio of swept area, plate area to swept area. And on the other extreme, this is also called a western mill, because they used it to pump water in the American West. And well, this is also what the Nazis wanted to develop. So similar technical use. And what you see here is a windmill, a wind turbine. It looks like a classic windmill, hundreds of years old windmill, but it's not. It was actually built in Denmark by Joule, and is considered, so uses lift here. So these blades, they are different from usual ones. Also 6 there. This is a historic photo of a windmill that's in between, and actually also the Dutch windmills. They have a not so large ratio of blade area to swept area, And so you get that in some sense these were modern windmills, and perhaps I make a few more historic remarks on the Dutch windmill in the last lecture of this course, if time permits. So this is the Hütter diagram. Let's come back to the, we just write it, that's what it is, Hütter diagram. And as the last point here in this chapter, we have a brief look at the angle at which the at which the airfoil profile is or has to be placed. So let me explain this with a graph, with a diagram. Yeah, this here. Yeah. So the point here is, at which angle should we place the airfoil? So, you know, if we have an airfoil like, say, like this, an airfoil like this, then you know that the angle of attack, so that we have a certain angle of attack. So this would here be, if the wind comes from here, then this here would be the angle of attack. And now, if you change the angle here of this airfoil, then lift can be larger, right? And for wind turbine blade, the situation is always a little bit more complicated because there is also the velocity, the local velocity of the airfoil profiles. So I try to depict this here. So here is one plate. This is not the one that's important. So what you have to consider is a plate that's perpendicular here on the drawing blade, on the drawing plane, I wanted to say. And well, we assume this wind triangle. Yeah, so we have wind coming in parallel to the axis of the rotor, and we assume that this rotor blade here rotates here out of the plane of drawing, and eventually arrives here. So it has a velocity in this direction, and therefore the wind has a velocity in this direction. So this is at least this the wind component parallel to the rotor plane, and then the effective wind direction is this one here. So now we know that that lift is always perpendicular to the wind direction, and drag, of course, parallel to that. And then we would place our air. We would ask, say, for this angle of attack, and then we have to build in the profile appropriately. And you know that this triangle here changes with radius, so this means that we need to twist the rotor plate appropriately. And well, this insight is by no means new. It was new to derive it mathematically, but actually, back in the 19th century, if not the 18th century, it was Smeaton, this was already experimentally established. And it would be easy to derive a simple formula for this angle. Okay, so far for chapter, which chapter was it? I think 6. Yeah, so this was chapter 6. And now, of course, chapter 7 But the purpose of that chapter is to look at the impact of losses. And we'll first try to contemplate which types of losses we have, and then we would try to find expressions for the magnitude of these losses, and see by how much it reduces the efficiency of a windmill. We already established that we can at most get 16/27, so roughly 60% of the kinetic energy of the wind. And of course, this 60% will further be reduced. And the nice thing is that it will actually be possible to put numbers there. So to really say by how much will it be reduced for realistic qualities of the blades. Okay, let's start with this and write a headline: 7, impact of losses. So a few words along the lines of what I just said. So the bed's power coefficient CP beds equal to 16/27 can only be reached by a hypothetical ideal machine. Yeah, in reality, several loss mechanisms should be considered. And if you think about last lecture, one is already obvious. And actually we said it already at that time. Yeah. Obviously, we neglected drag, and we did it pretty explicitly. So if we look back here, where was it? Yeah, here. Right. So here we said, in this chapter we neglect drag. So what we neglected was this term. Right. And it's obvious that we have to deal with it in this chapter. But there are other loss mechanisms. Actually, in total, there are 3. And the first one is what we call airfoil losses. And what we mean is drag. Yeah? So what we neglected was drag for this force component parallel to the rotor plane. Yeah? And this was equation 638. The next one are tip losses. This is another nice story. Not so easy to quantify. Yeah, so we'll use a heuristic formula that goes back to Brundle again in order to determine this. Let's just say tip losses. I'll explain the physics later, and instead continue with wake losses. Yeah? So what we said is that what a windmill does is that it decelerates the air that streams through the rotor plane, right? And what we assumed was pretty much that the air streams through the rotor plane and keeps its direction. Well, this can't be quite right because we saw that it needs more air, more space, because it gets slower. But this is not the only thing. What we also saw was that the air, of course, exerts force on the plates. In particular, it exerts this force parallel to the rotor plane, right? And now we remember from the first semester, we remember Newton's third law, which says that actio equals reactio. So this means that there is also force exerted by the blades on the wind, which means that they are deflected not only in a radial but also in tangential direction, right? And this is called wake losses. Yeah? Let's quickly write it down. The wind behind the rotor plane has velocity components perpendicular to the inflowing air. Yeah, I say here perpendicular, but what I mean specifically is the component parallel to the rotor, so the tangential rotor velocity component. Yeah. Okay, so we start with airfoil losses. 7.1 airfoil losses. It's clear what we have to do. I mentioned already the term that we neglected, so we have to deal with this term. But let's write a few words before we start to do so, because we want to, we want to think about where airfoil losses are particularly relevant. As long as the optimum blade geometry so if we are only looking at the optimum blade geometry, then our goal is obviously a different one as compared to the situation where we try to really attach an efficiency to the windmill. Yes, so the efficiency was not the point in the last so for the BETS design, but now we have to take a different approach because we want to say something about the efficiency of a realistic windmill, of a real windmill. So as long as the optimum blade geometry is the only concern, it is reasonable to neglect track because the lift coefficient is much larger than the drag coefficient. Yeah? However, in order to establish a power balance sheet, drag needs, of course, to be included. Yeah? Later we'll see that actually this third mechanism of losses, that this will also have an impact on the design of the blades. But here for the drag losses, this is actually not the point. It just costs power, whereas these losses here, of course, also cost power, but they also need to lead to a modified air plate design, at least close to the rotor hub, to the rotor axis. So let's try to find an approach. So what we define is the efficiency of an airfoil, and we say that the efficiency of the airfoil is just the ratio of the power delivered if we consider drag and if we don't consider drag. And we calculated, of course, the power without drag already, and so we just need to quantify this ratio. So we define the airfoil efficiency. And we call it as usual eta. It also has a prime. I don't remember why it has a prime. Yeah, so that's the airfoil efficiency of a blade element and we do it as I just explained. So eta prime airfoil. This is power with drag divided by power without drag. And now we use this equation that I repeated already. This was equation 636 according to my notes. So let's check whether this is true. This is true. Yeah, so look here. This is this equation. So according to equation 636, this is Ca times the sinus of alpha minus Cw times the cosine of alpha divided by the thing without drag, right? So we have Ca times the sinus of alpha, and this can be written. So I said power with and without drag, but what I wrote is just the thing that's proportional to the force, but of course power is also proportional to the force, and therefore this is of course right. So we have 1 minus Cw divided by Ca times the tangent of alpha, and now remember the glide number, which is the ratio of the Cw to the Ca value. This is 1 over epsilon times tangent alpha. Yeah? And this is the glide number. Yeah? Glide number, we had a few examples, right? So 40 is a respectable glide number. 60 would be extraordinary. Yeah, so 40 40 seems to be a good house number for that. Okay. So next thing is that we try to replace this tangent alpha here. And of course, we had a formula for that. And according to my notes, it's 33. Let's go back. 33. Of course, I checked it before the lecture. So you find it here. Right? And what it basically is, it basically comes from 31, from this equation, which is just a consequence of these wind triangles. And the only thing that we did was, well, to replace the velocity and the omega, and particularly the omega, by the tip speed ratio, right? So, and this we plug in now here. And if we do so, so using equation 33, let's write it nicer. Yeah? So we replace tangent alpha by 2/3 of radius of the windmill divided by the tip speed ratio, the design tip speed ratio divided by R, which is equation 33, right? And then we find that eta airfoil is equal to 1 minus 3/2 R divided by capital R, lambda A divided by the glide number. So that's equation 1 in this chapter. And now we can, so now you should appreciate that we already achieved something that's actually quite nice. Namely, we have the efficiency in the form of 1 minus the losses. Yeah, so it's immediately clear that these here are the losses. Yeah, strictly speaking, the relative losses. Yeah, so equation 1, gives evidence that the relative losses, the relative loss due to drag is Xi airfoil is equal to 3/2 R divided by capital R lambda A divided by epsilon. Yeah? Trivial insight, but of course important. Yeah? So now we have the losses, the relative losses actually for a plate element. Yeah, so everything that we did so far was for a plate element. And now we have to integrate over the radius in order to find the entire losses. So equation 2 is the loss for a blade element. dr, in order to find the entire losses, we have to integrate. Right? And what we would find then is that that the power that includes the power including drag losses now what do we expect? We expect, of course, the Betz power minus the drag losses. Yeah? And this power should have this form. Yeah? So this would be P Betz times eta airfoil. Yeah? So now I remember what the prime means. The prime corresponds to the losses for a blade element. And now here we have the total losses, the integrated losses. So let's write down the Betz power. So this is 16 over 27 times rho over 2 velocity wind speed cube. And then we have the area. So now we would integrate all the rings, the ring elements that make up the area swept by the rotor. But now here we include actually the efficiency. So we integrate from 0 to capital R the airfoil efficiency times, the ring element circumference times the thickness of these ring elements. Yeah? And now we can substitute equation 1. Yeah, so this equation here, and just calculate it. Just do the integral. So we have 16 over 27 rho over 2 V1 cube, and then this integral from 0 to capital R, 1 minus 3 over 2 R over capital R, lambda A over epsilon, and then we have 2 pi R dr. Yeah, that's an easy integral, and the result is 16 over 27 rho over 2 V1 cube R squared pi. This is what we would have without the losses, right? And now with losses we have 1 minus lambda A over epsilon. And I would say that this is an extremely beautiful formula, because all the complications that you would expect from such a complicated phenomenon like drag, well, it is just in this. Factor here, right? So what we have here is just the tip speed ratio divided by the glide number. Now you could ask, does it make sense? Now, of course it makes sense, but why? Well, the higher the tip speed ratio, what does it mean, a high tip speed ratio? High tip speed ratio actually means that, that the wind velocity is large, right? So, and if the wind velocity is large, then the relative wind velocity, I should say, so the relative wind velocity between blades and air, so this is large, and therefore, of course, also drag is large. However, if epsilon, if the glide number is large, then of course you have very high quality airfoils, which are probably also expensive, so this makes this looks reasonable. Okay, let's write down this comment. So this is a beautiful result. So the total losses, this is what we calculated. The total losses due to drag are simply given by the ratio of tip speed ratio, by the ratio of tip speed ratio and glide number. And it makes perfect sense as we discussed. Perhaps a few more remarks on CW value. I mentioned that already 2 or 3 lectures ago. We discussed the CW value, the drag coefficient. But now I found, I stumbled over a few things that I found funny and I wanted to share with you. Well, the question is whether they are really funny. But I found on the internet the following. So this was an advertisement by the Ford company. And they advertised their new truck. It's not their biggest truck. It's actually one of their smaller trucks. Yeah? So it's a F140. And they brag tough looks, cheat the wind. Yeah? So they advertise the low CW coefficient. Yeah? So just 0.36. Yeah? And well, this here is pretty much the state of the art, right? So this is a BMW, but if you take a Tesla or so, it will have similar values. Yeah, not all small cars are like that. But anyway, drag is not only proportional to the drag coefficient, but also proportional to the area covered by this vehicle. And you see that there is also pretty much of a difference. I just looked up the height and the width of these vehicles. Yeah? And what you find is that so that the drag losses of this car are twice as large as this car, or in other words, you can drive this car square root of 2 times faster than this car. And this is probably what we do in Germany, right? So that we drive square root of 2 times faster than this car. But actually, in Germany, we also have, we are also building stupid cars like that. I looked up an Audi Q8, right? And it has interestingly a similar drag coefficients of 0.36. I thought that they would be better. So this is a truck, so it has a open back, so a loading thing, yeah. And I thought that this should make a larger drag, but actually these SUVs apparently also have a pretty high drag coefficient, but they still would, so there's no speed limit on German autobahns, and Audi Q8 would drive probably as fast as a BMW, right? And then, of course, I'm not sure whether German cars are more fuel efficient than American cars. And so when I lived in the US, I always looked at these cars and I shook my head and thought, the Americans are crazy, but I think we Germans are as crazy. Good. I think this is a good point to make a short break, and we will continue with the second type of losses. In 5 minutes, I hope you have a tea prepared or something like that, a snack. See you in 5 minutes. let's continue. So we did the first of the three losses. Now let's come to the next one, tip losses. I didn't want to explain too much because, well, I will explain it now. Let's start by just writing the headline and perhaps even also write down a few of the physics insights that lead to this problem here. So 7.2 tip losses. So the idea is the following. I start with a few pictures, with a few graphs. So maybe this one here and another one. And so what you see at this graph is, of course, this airfoil. And also depicted here are the pressure conditions. Yeah, so you see more pressure than positive pressure here on the lower side of the wing, and here negative pressure on the upper side of the wing, which is of course just in other terms the lift. By the way, I switched on Zoom again. If nobody is there, they switch it off, and then we don't have a back channel. Kind of pity, but it's your choice, of course. So now, once again, we have negative pressure here and positive pressure here, right? Now let's look at another picture. So this one, I apologize for it. I did it myself. It doesn't look very good, but I think it's good enough for the purpose that we need. So I have here the fuselage of an airplane, right? And I have here the wing, the airfoil. And what we know now is that on top of the wing, the pressure is low, and at the bottom, it is high, right? But now they are here at the tip of the wing. We speak about tip losses. At the tip of the wing, yeah, so there is nothing, geometrically nothing, that prevents air at high pressure to compensate the low pressure at the upper side of the wing. Yeah? And accordingly, if you would now look for the lift coefficient, then strictly speaking, you would say that the lift coefficient is large here, but here at the tip, it should reduce. It should go down to zero, right? It should have kind of this dependence, right? And these are obviously losses. Okay, yeah. So let's write a few notes about that. So in the same way, as for the airfoil of an aircraft, there is kind of a short circuit for the air at the tip of the blade. Of a short circuit for the air at the tip of the plate. So actually, for a windmill, we have an advantage as compared to an airplane, because for an airplane, or let's say for a wind turbine blade, the blade gets, of course, thinner and thinner the closer you come to the tip, and therefore the amount of short circuit, so to say, is smaller as compared to an airplane. But of course, for an airplane, they kind of do this a similar trick, by making the airfoils, the wings narrower and narrower. But of course, for a windmill, we saw what the reason is. So it's not the tip losses; it's the fact that we want to achieve the Betz limit. So the situation is a little bit different, but nevertheless, these losses are there, and one has to try to to quantify them. But let's continue to write a few things up here. So this leads, as indicated here, this leads to decreasing lift coefficient towards the tip of the blade. And another consequence, which is actually quite interesting to see, is the following. So what you produce here is perhaps right. So we said that there is positive pressure here, negative pressure here. So you produce wind in this direction, right? So what you produce are vertices. And these vertices, they are actually, for airplanes, they can actually be used in order to produce an additional contribution to lift. But they also have quite negative consequences. And I want to show this here on a short video and a few other pictures. So this is a short video. What they did was to place some smoke, some colored smoke on the runway of an airport or so, or a test runway, I don't know, right? And now you see an airplane comes, commercial airplane, goes through this smoke, and you nicely see these vortices, right? And of course, pilots see this perhaps more often. And so here's a picture. I guess this was taken by another pilot or from ground. I'm not sure. Right? Now the question is, what can we do against that? So how can we reduce this this short circuit that we see here? Right? And this is actually known since a long time, but only in the 70s or in the 70s research started on that, and to my knowledge it's the gliders who first really used it and figured it out. But actually very early airplanes from the Second World War already had devices like that, namely winglets. So when I did my first air travel as a PhD student in the 1990s, most airplanes didn't have winglets, and then I have the wrong the wrong thing here. So this one I wanted to show. Yeah? And then the first aircrafts had winglets like this here. Right? And you see that they are supposed to reduce these vortices and this kind of short circuit. And newer types are look like this. Right? So very different for different airplanes. I just read that for the for Airbus 380, the winglets were supposed to be so large that they didn't fit to airports, and so they had to change the design or something like that. Here you see a very modern form on a pretty infamous aircraft, the 337 MAX, and it has this kind of a split tip winglet. And they say, Boeing claims that alone this year reduces the fuel demand by 1.5%, which is a lot. Yeah? And sure enough, also windmills have winglets. So they are very hard to see. And when I first gave this course 10 years ago or so, and read about tip losses, I wondered whether windmills do have actually these winglets. I was looking for that. It's actually pretty hard to see them, so you need binoculars if you are not too close to such a windmill. But interestingly enough, also my small model here of a windmill has these winglets. So maybe you see it here. Okay, good. So this is how people try to reduce the tip losses. But now let's try to calculate these losses. By the way, another interesting thing to know, these vortices, they can actually be quite dangerous. So if you have a heavy aircraft, then it produces, of course, a lot of these wake vortices. And you can imagine if there's a small aircraft following a large aircraft, so this can be huge a huge danger for a huge threat for a small aircraft. I just in preparation of this lecture here, I just read about an incident over Arabia. So there was also a heavy aircraft and a small business aircraft was following, and it lost 10,000 feet of height, and one engine was damaged, and the interior of this airplane was completely messed up because the airplane rolled several times before the pilot managed to stabilize his aircraft again. So there were several incidents actually with small airplanes or smaller airplanes following larger airplanes. So a glider following or crossing the wake of a military aircraft. This is of course very dangerous for gliders. So another thing was that after such an incident, they actually increased the time between a 757 because this airplane happened to produce more wake turbulences than anticipated. And then after an accident, the distance between an aircraft following a 757 was increased. interesting fact to know. Oh, what's that here? So, let's continue. I said that we have kind of a heuristic approach to deal with this, and what Brundle arrived at was that what's happening is that the effective length of the blade, or the wing, is reduced by a certain amount for which he gave an equation. So in this approach we want to follow. So a simple approach to capture the tip effect is to use an effective rotor diameter. We call it D prime instead of the actual diameter. So, and Brundle gave the estimate that D prime is equal to D minus 0.44, and now some quantity B, and this quantity I want to define using another figure here. This one. So what you see here are a number of blades. So this is not a realistic view of a wind turbine. So for the wind turbine, if one blade sticks out of the drawing plane, like indicated perhaps here, then the other would go. So it's rotated by 120 degrees, so it goes into the drawing plane pretty much, so at a certain angle, and of 30 degree, of course. But just to see how this is defined, so it's the distance of the blades. And actually, it's the projected distance of the blades. So projected on the wind direction, on the effective wind direction. So let's continue the sentence here, where B is the projection of the distance A between rotor blades. The projection of the distance A, so this is this quantity here, between the blades. And the projection on a plane perpendicular to the wind direction C, the effective wind direction C. And we can calculate this when the number of blades is capital N. B is given by so we have B is equal, now we need, of course, the circumference. So pi times D divided by N, so this is A, times the sinus of alpha, as defined in the figure, so as usually defined, so as we defined it all the time. Okay, now we need to replace sinus of alpha, for example. Yeah, we want to have a closed form for a closed expression for that. And to this end, we look at wind triangles again. Wind triangles. Let's see. So this one here. Yeah, so from the figure, we read an expression that we already had, namely that C times the sinus of alpha is equal to V2, so the wind speed at the rotor plane, yes. And we have C squared is equal to omega R squared plus V2 squared. Yeah? And then if we use, I say here equation 5, yeah, so I should give it a number here. Yeah. Then this is probably equation 6. Yeah. So what we find then, yeah, if we use 5 here, is D prime is equal to D times 1 minus 0.44 pi over N V2 divided by C. And now here we replace V2 is equal to 2/3 of V1. And then we get D times 1 minus 0.44 times 2/3 pi over N, and now V1 over C. Yeah? And what we do next is to calculate in a short auxiliary calculation. We calculate this ratio. Yeah? So auxiliary calculation, compute V1 over C. And what we find is V1 over C is equal to 1 over the square root of the tip speed ratio squared plus 4 over 9. That's a very similar calculation we did already when we calculated the Betz design. So, and then we get that D prime is equal to D 1 minus 0.44, 2 over 3 pi over N, and then this ugly expression here. Yeah? But the nice thing that you see, and you realized it, of course, already, well, probably at this point, is that again we have this nice form that we have 1 minus something. Yeah? So this is the Betz condition, and here this is the addition of the tip losses. Yeah, it is of course clear that if you reduce the radius of your wind turbine, then you don't catch as much wind as if you don't do that. And this, of course, is a reduction in power, and therefore a reduction in efficiency, or a form of loss. So now we calculate the loss. Yeah, so the power of a wind turbine is proportional to the square of the rotor diameter. And this means the efficiency loss due to surround flow or bypass flow is, so we have eta tip equals d prime over d squared, right? And what we have then is 1 minus 0.92 divided by n times, and now this square root here. And this 0.92, this is equal to 0.44 times 2 over 3 times pi. Makes sense? Pi is approximately 3. And so it cancels with 3 approximately, times 2. So 2 times 0.44 is approximately 0.92, isn't it? Okay, now we can simplify it a little bit more, just remembering the conditions that we actually have at a wind turbine. So we said that the typical tip speed ratio for a wind turbine is on the order of 7 or so. Yeah. So now if you look at 7, so if you put here 7, then the square is 50 or so. Yeah. And 50 is much larger than 4 over 9. Yeah. So 49 as compared to 4 over 9. So we can simplify this a little bit. Typical modern windmills have lambda A on the order of, say, 7. Since 7 squared is much larger than 4 over 9, we can approximate n tip is equal to 1 minus, oh, I forgot a square, I realize. 1 minus 1.84. There's also no comment on YouTube, so nobody noticed. No. N times lambda A. right? Good. This is equation 8, and of course I used no, I didn't do that. Sure, I did. Yeah. So what we have here is so 1 minus this thing here squared, and we need a power series expansion in order to arrive at this. Yeah. So what I used here was 1 minus x squared is equal to 1 minus 2x. Yeah. So this is what went in here. Okay, and therefore we can say for the tip losses, yeah, so it's of course this second term here. So the tip losses this would be Xi. Tip is 1.84 divided by n times lambda a. Right, trivial, considering of what we did already. Okay, again, here are a few comparisons of different windmills. And I have a table for that I just copy into this script here. Hopefully no, unfortunately I forgot to copy it to the iPad. Ah, that's unfortunate. So I have to do it here. So a table. So a Western mill, then I will have a Dutch windmill, a Danish turbine, older version, and then a one-blade turbine. So these things were built for experimental purposes. And obviously, a one-blade turbine will have a very large lambda A. Right, and we will look at lambda A at the number of blades, at the tip losses, and on T over D. Okay, so let's write that down. What we want to: a Western mill, a Dutch windmill, a Danish turbine, one blade, and a more than 3 blade. As a Danish turbine, this means these turbines that were built so pretty much after the war by, now I forgot the name, so one of the pioneers of windmills. So lambda A for the Western mill is 1. So for the Dutch, for the old style, hundreds of years old Dutch windmills, it's 2. The Danish turbine, 6. So pretty modern windmills already. So for one blade turbine, so these experimental turbines, 12, and here 6.5 or so. The number of blades N, this would be here 20 or so. For the Dutch windmill, as everybody knows, 4. The Danish turbine was the predecessor of all modern windmills. So this is the Danish design that we use today. Of course, for a one-blade turbine, it's 1, and for 3 blades, of course, 3. Right? And now we see that we have here in the denominator n times lambda A. So we write that down here, and we find here 9, 22, 10, no, that's nonsense. So 1 times 20 is, of course, 20. Then we have 8 here. Here we have 18, here 12, and then here, 20 more or less. And accordingly, we can calculate the tip losses. So this is this key tip. And we find here 9, 22, 10, 15, and 9. Right, so so you see why windmills were optimized in the way they were actually optimized. So the Western mill is not very efficient because it has the tip speed ratio is too low, but you see this optimum here and of course here, right? So the loss is so 5%, then we have more than 10% here, and these are the modern values. So I'm not sure why they tried out the one blade design. Doesn't make much. So they would use a counterweight on the other side, just in order to make it run. So the idea was of course to have as high tip speed ratio as possible, but I don't really see the point. So if you find a note somewhere in the literature why they did this, then let me know. Okay, so we are done with the tip losses, and now wake rotation. This is the final one. 7.3, of course, it will not be possible to finish this today. So actually, we will use pretty much of the entire next lecture in order to cover this in full detail. But we can already start to write a few things down, just that we have a quicker start next time. So wake rotation. I explained already that that the wind, of course, exerts a force on the blades. So that's the entire purpose of building such a windmill. But, and that's not the purpose, but unavoidably this happens, that the blades exert forces on the wind, and therefore the wind is deflected in a direction parallel to the rotor plane. But what we mean here in particular is in a direction, not the radial direction, not the direction parallel to the blades, but in the direction perpendicular to the blades. So perpendicular to the rotor axis and perpendicular to the blades. So this is the tangential direction. So let's write that down. So first, the Betz analysis assumes parallel flow to the rotor axis. So if you look a little bit carefully, then it actually assumes so more precisely, it assumes only expansion of the air, let's say air volume in radial direction. Let's call this ER. right? And the other direction, parallel to the rotor flow, you could say EZ. Okay, yeah. So tangential velocity components so tangential velocity components v theta are not considered. So now let's look at the situation also with an equation. So if we look at the expression for the power, then we have, so this was equation 642 according to my notes. So then we have for a plate element dP equal to n times the parallel component of force times omega r, right? So force times velocity. So this is here the force in direction of the blade velocity and this here is the blade velocity. Yeah. Yeah. And what this equation says, if you look at it, is that you can get high power either by high velocity and modest force, or you can achieve high power by large force and modest velocity. And actually we have both situations for a wind turbine. If we are closer to the tip, then we know that the blade velocity is very large, right? And therefore the lift force is rather low, right? And close to the rotor axis, it's vice versa. But if you think about what I said before, namely that the thing that we are looking at here is Newton's third law, namely that the force, so this term here, so that the force exerted by the wind on the blade is equal to the force exerted by the blade on the wind, then you immediately realize that this wake rotation is more severe, is more pronounced closer to the axis and less important closer to the tip. And so it's kind of nice that we have three loss mechanisms. This third one only applies for, or dominates only close to the rotor axis, and the other two, they dominate for closer to the tip. And so next time we will calculate this, and actually this wake rotation will also lead to a modification of the blade geometry, of course close to the axis. And this is called the Schmitz design. And of course I will also introduce Schmitz in the next lecture. So time is up, I think. Thank you for your attention. If you have questions or remarks or just want to discuss the one or the other thing, Then we'll have a question and answers session in a few minutes, so at 6. I would be delighted if the one or the other of you. Thank you for your attention, and see you next week, if not in a few minutes.